Good morning, dear students. In the last class, we started applications of Gauss theorem. The first two applications we discussed in the last class. I told you that we have one more application, that is a third application. So today in this class, let us discuss the third application of Gauss theorem. The third application is electric field due to a uniformly charged thin spherical shell by using Gauss theorem. The first two applications we learned that the first application we discussed and we derived the derivation for electric field for uniformly charged straight infinite wire or a conductor. In second application, we found that or we derived the expression for electric field for uniformly charged thin plane sheet. The same way, now in this class, we are deriving expression for electric field due to a uniformly charged thin spherical shell by using Gauss theorem. So to derive an expression for electric field, have to consider a spherical shell or a spherical conductor. Look at the board. I consider one spherical conductor or thin spherical conductor having surface charge density sigma. Surface charge density sigma. In this third application, we have three cases. Look at the first case. When point P lies outside the spherical shell, and the second one, when the point P lies just outside or on the surface of spherical shell. One more case we have, that is when a point P lies inside the spherical conductor, which means we are finding the electric field outside the spherical conductor, on the surface of the spherical conductor, inside the spherical conductor. So let us discuss one by one. The first case, when point P lies outside the spherical conductor or a cell. So in this case, small letter r greater than capital letter R. You will get to know what exactly the small letter r represents and capital letter R represents. Look at the diagram. So here I consider a spherical conductor of radius r, capital letter R. The white chalk what I used, that indicates spherical conductor of radius r, capital letter R, having surface charge density sigma. Spherical conductor of radius r, that is capital letter R, having surface charge density sigma. Now according to the first case, we are finding the electric field outside the spherical conductor. Now outside the spherical conductor, to calculate electric field or to find the electric field, I must consider a spherical Gaussian surface. So look at the dotted line over the spherical conductor by using pink color chalk that represents Gaussian surface of radius small letter r, of radius small letter r. On the surface of the Gaussian surface, we marked a point P. In that point P only, we are calculating electric field due to spherical conductor at a distance r, the small letter r. So here capital letter R is the radius of the spherical conductor and small letter r is the radius of the Gaussian surface. At this point P, we are finding electric field due to the uniformly charged thin spherical conductor. Okay. Now by using this diagram, we have a small derivation. Now according to the Gauss theorem, or Gauss theorem states that, or it deals with total electric flux. So electric flux through the Gaussian surface we are calculating now. Here I will write electric flux through the Gaussian surface. Through the Gaussian surface. Total electric flux through the Gaussian surface. We know the equation for electric flux, that is phi is equal to E A cos theta. E A cos theta, electric flux equation. Look at the diagram. We know that the direction of electric field is always normal to the spherical conductor, means which is directed outwards, the electric field. If I consider a small area element over the surface of the Gaussian surface, to that area element, if we return a area vector that is also directed outwards, so both are parallel to each other. The direction of electric field and the direction of area vector both are parallel to each other. So theta is equal to 0 degree. Theta is equal to 0 degree. So cos 0 degree is 1. So phi is equal to E into A. So phi is equal to E into A. A represents surface area of the sphere. Surface area of the sphere. So surface area of sphere. Since we consider a spherical Gaussian surface, phi is equal to E into, what is the surface area of the sphere? 4 pi r square. Which r I supposed to write, capital letter R or small letter R? We need to write small letter r. Why? Because the point where we mark, that is on the surface of the Gaussian surface at a distance r. So I suppose to write small letter r square. So phi is equal to E into 4 pi r squared, that is surface area of the sphere. We are marking equation number 1. Then from Gauss theorem, we know the equation Q divided by epsilon naught. Equation number 2. Now we got equation number 1, equation number 2. On comparing equation 1 and 2, just compare equation 1 and 2, what you will get? E into 4 pi r squared is equal to Q divided by epsilon naught. I am simplifying the equation for E. Then E is equal to Q divided by the 4 pi r square will come to the denominator, that is 4 pi r square epsilon naught, or we can write like this, E is equal to 1 over 4 pi epsilon naught Q divided by r square. So this is the magnitude of electric field when the point P lies outside the spherical conductor. E is equal to 1 over 4 pi epsilon naught Q divided by r square. Here one thing you can notice, here I have written small letter r is greater than capital letter R. You just go through with the diagram. Small letter r is greater than capital letter R, which means we are finding the electric field outside the spherical conductor. We will move on to the second case. Case number 2. When point P lies just outside or on the surface of a spherical conductor. So in this case, R is equal to R, that is small letter r is equal to capital letter R. Look at the diagram, you will get to know. Again I consider spherical conductor, uniformly charged spherical conductor having surface charge density sigma. Since we are finding the electric field on the surface of the spherical surface, look at this, on the surface of the spherical conductor I consider one Gaussian surface just outside, which means it's not exactly on the surface of the spherical conductor, just outside. So approximately small letter r is equal to capital letter R. Look at the diagram. Small letter r is equal to capital letter R. The same derivation we are deriving. Again, electric flux through the Gaussian surface. I will write here. Electric flux through the Gaussian surface. Same equation, phi is equal to Ea cos theta, again theta is equal to 0 degree. Normal to the surface, the direction of electric field is normal to the surface, and area vector is also normal to the area elements, both are parallel to each other. So theta is equal to 0 degree. So phi is equal to E into A. Again A represents surface area of the spherical Gaussian surface. I'll write here. So phi is equal to E into surface area of the spherical Gaussian surface is 4 pi. So here I need to write capital letter R. Why? Because small letter r is equal to capital letter R. So R square equation number 1. So we make it as equation number 1. Then from Gauss theorem again. From Gauss theorem we have an equation phi is equal to q divided by epsilon naught. Mark it as equation number 2. Again we are comparing equation number 1 and 2. On comparing equation 1 and 2, we are comparing equation 1 and 2. Left hand side is same, so only we are writing right hand side A into 4 pi capital letter R square is equal to q divided by epsilon naught. Keeping E here only, I am taking 4 pi R square to the right hand side. So E is equal to q divided by 4 pi R square epsilon naught, or we can express like this, E is equal to 1 over 4 pi epsilon naught q divided by R square. So this is the magnitude of electric field when point P lies on the surface of spherical conductor or just outside when small letter r is equal to capital letter R. Here one thing you can notice, so whatever the steps I followed, the same steps we are using, but the thing is instead of small letter r I am using capital letter R, that's it, everything is same. Now case number 3. So in this case when point P lies inside the spherical conductor, which means we are finding the electric field inside the spherical conductor. Look at the diagram. So I consider spherical conductor having surface charge density sigma. So inside the spherical conductor have consider a spherical Gaussian surface which is indicated by dotted line. The radius of the spherical conductor is capital letter R and the radius of the spherical Gaussian surface is small letter r. Look at the diagram, you will get to know that small letter r is less than capital letter R because we are finding the electric field inside the spherical conductor. And we know that from the basic properties of electric charges we learned that electric charges always resides on the outer surface of a charge conductor. So inside the charge conductor electric charges is 0. So as there is no electric charges inside the spherical conductor, electric field also 0. For that derivation is not required, directly you can write E is equal to 0, but let we have a derivation for that. Electric flux through Gaussian surface. Again the same equation, phi is equal to Ea cos theta, theta is equal to 0 degree, the same what we followed in the first case and second case. The remaining phi is equal to E into A. So phi is equal to E into surface area of the Gaussian surface, because the point P is inside the spherical shell. Inside the spherical shell means here. What is the distance between the point to on the P? Small letter r. So what I am supposed to write? 4 pi r squared, equation number 1. Then from Gauss theorem, we know that the equation phi is equal to q by epsilon naught, but q is equal to 0 because inside the spherical conductor q is equal to 0, so phi is equal to 0. So we can make it as equation number 2. So compare equation number 1 and 2, you will get, and comparing, here we can write 0 by epsilon naught itself, and comparing equation 1 and 2, you will get E is equal to 0, is equal to 0. So inside the spherical conductor, electric field is 0. Third case, when point P lies inside the spherical conductor, small letter r is less than capital letter R, then electric field found to be equal to 0. So these are the 3 cases by using spherical conductor, uniformly charged spherical conductor. Case number 1, electric field outside the spherical shell. Case number 2, electric field on the surface of the spherical conductor. Case number 3, electric field inside the spherical conductor. So all the 3 cases I am going to represent through this graph, means graphical representation of variation of electric field with distance. How does the electric field varies with the distance? Look at this graph. I consider spherical conductor having surface charge density. You can write here uniformly distribution of charge. Here the x-axis represents distance, y-axis represents electric field. Electric field inside the conductor is 0, E is equal to 0. Look at this, note 1, when small letter r less than capital letter R, then E is equal to 0. Look at this, small letter r less than capital letter R means electric field inside the spherical conductor 0. Then when small letter r is equal to capital letter R, that is when the point P lies on the surface of a spherical conductor, we got the equation like this. So E is equal to 1 over 4 pi epsilon naught q divided by capital letter R square. So electric field is maximum because on the surface of a spherical conductor electric field is maximum. When small letter r greater than capital letter R, that is when the point P lies outside the spherical conductor, we got the equation like this. E is equal to 1 over 4 pi epsilon naught q divided by small letter r square, which means electric field is inversely proportional to the distance, means as the distance increases electric field goes on decreasing. Fourth point, when r is equal to infinity, then electric field is 0. Why? Because electric field keep on decreasing as the distance increases. First chapter is completed. Now I am going to give most important and expected question. Please make a note and practice the derivations that will be useful for your examination. The first chapter, electric charges and fields, got over. Here you have most expected and repeated question as your assignment. Please keep or maintain a separate book and try to write an answer for this and practice the derivation. 1 mark question, most expected and repeated question. What is SI unit of charge? You need to write the SI unit of charge. What is SI unit of electric field? State Coulomb's law, only statement because it carries only 1 mark. What is an electric dipole? Statement. Then 2 mark questions, state and explain Coulomb's law in electrostatics. When you come to 2 marks, you need to write the statement and the expression. Sometime they will ask the question to express in terms of vector form. that carries 2 marks. Then sketch the electric lines of force due to a point charge Q if Q less than 0 and Q greater than 0. We studied properties of electric lines of force. There, what is the nature of electric field in case of positive charge, in case of negative point charge, we studied. There you will get to know the complete picture about the electric lines of force. Then give the 3 properties of electric charge or electric field lines. See here I mentioned 3 because this question may ask for 2 marks or 3 marks. Mention basic properties of electric charges, any 2 for 2 marks, any 3 for 3 marks. Similarly, mention the properties of electric field lines or electric lines of force. If they asked only 2 properties, it carries 2 marks. If they asked 3 properties, you need to write 3. Then similarly we have 5 marks question. Expression for electric field at a point on the axial line or equatorial line of the electric dipole, any one, either axial line or equatorial line, the whole derivation is supposed to write. The second one, state Gauss law in electrostatics. They can frame for 1 mark also, or in the 5 marks question itself, state Gauss law question mark and applications. Along with the applications, we learned 3 applications. Electric field due to uniformly charged thin straight infinite straight wire. Electric field due to uniformly charged infinite plane sheet. The final third application, electric field due to uniformly charged spherical conductor. All the 3 applications are very important for 5 marks along with this statement, state Gauss law. So for the time being, so these are the questions I am giving. Please keep a separate book and write the answers. So theory part is completed, but still we have a numericals and the first chapter. We will see, if possible, we will start from the next class, or else straight away I will move to the second chapter. We will meet in the next class. Until then, take care. Have a nice day. Thank you.